Yeah, that's right.
That's fine? Okay, cool. So thanks to be here. Actually, I'm not going to give this talk, right? So as you can imagine. So Haoyuan Li is there online from SF. So, yeah, hello. So I will leave in the ground between codes and, okay, go on, dude.
All right, thanks, Andy. So, hey guys, sorry I couldn't be there due to some visa issues. So I'm going to give this talk remotely to introduce Tachyon as well as its use cases. So here's a slide. So the presentation is to introduce Tachyon, which is an open source memory-centric distributed storage system. And I'm Haoyuan Li from Tachyon Nexus. People also call me HY. So who am I? So I'm a co-creator of Tachyon, and now I'm the CEO of this company called Tachyon Nexus, which is a company keep pushing Tachyon forward as well. So I was a PhD candidate from UC Berkeley AmPlab, where I created Tachyon as my PhD thesis. So a little bit about the company at the beginning. So Tachyon Nexus is formed by the team, by the Tachyon creators and Tachyon top contributors. And we got Series A funding from Andreessen Horowitz, and we are committed to do the Tachyon open source, push the Tachyon open source project. And at the bottom, that's our company website. And by the way, we're hiring as well. So here's the outline of the talk. So at the beginning, I'm going to introduction to Tachyon, and then I'm going to introduce some Tachyon use cases and the new Tachyon features were released in Tachyon 0.8. And in the end, I talk about how to get involved with this open source project. So let's start with the introduction. So here's the history of the Tachyon. So we started Tachyon back at UC Berkeley AmPlab from the summer of 2012, which is like 3 years ago. It's the same lab produced Apache Spark and Apache Mesos. And Tachyon was open source on the second year, April, under Apache 2.0 license. And the latest release is version 0.8, actually 0.8.2, which is like yesterday or today in your time zone. And it has been deployed at more than 100 companies. So here's so the project is growing pretty fast, just to give you a sense. So here's the community growth of the project. So in terms of number of contributors, at the beginning for V0.1, we had 1 contributors, and then we had 3 contributors in 0.2. Then we had 15 in 0.3, and then 30 in 0.4, 0.5 around 50, 0.6 more than 70, and then more than 100, and 0.8 we have more than 170. So now we have more than 170 contributors from more than 50 organizations, and it's one of the fastest growing big data open source projects. And I want to use this opportunity to thanks to our contributors as well as users. And this is a figure auto-generated on the Tachyon website. If whoever contribute to the Tachyon project, there will be a bubble showing here. And the more you contribute, the bigger the bubble will be. And on bottom, that's a part of the company which are using and contributing to the Tachyon project. And there are some recent reported usage, like Tachyon Fedora distribution. It's a default off-heap storage for Spark. And IBM said what the work they have done with Tachyon. And the pivot to the EMC said they believe Tachyon is the future, play the critical role for the data lake architecture. Yeah, I can hear you. Oh, that's weird. Okay, can you see now? Oh, yeah? All right. Oh, okay. So let me see if, okay. Let me try this way. Entire screen. So let me see. Can you hear? Can you see the difference now? Okay, great. All right. So I probably lost you guys from the very beginning, but anyway, so here's a community growth, and it's a lot of companies and contributors, and it's one of the fastest growing projects in the big data ecosystem. And here's the contributors and the users. You see the bubbles I mentioned earlier, and here are the companies which are contributing and using Tachyon. And this is some reported usage in Fedora distribution of the storage for Spark. Company are using it. EMC, IBM, they all endorse the system and doing work around the system. So then the question is, what's Tachyon? So it's an open source, memory-centric distributed storage system. So here's from the stack perspective where Tachyon sits in the stack. It sits between below Tachyon, there's all kinds of distributed storage, traditional storage like HDFS, like Amazon S3, OpenStack Swift, Ceph, this and that. And on top of that, you have all types of a computation engine like Spark, MapReduce, like Flink, like Impala. And then the question is, why use Tachyon? So here's the trend. So from the performance perspective, Tachyon is memory-centric, and memory is fast. RAM throughput increase exponentially every year. And on the other side, disk throughput increase slowly. Then you can see that memory locality is very important. It's a key to achieve very low latency interactive queries. That's a performance perspective. Then let's take a look at the price trend. So during the past like several decades, DRAM cost decreased exponentially. So every 18 months, the DRAM cost decreased around 50%. And you can see that at early 2000, Wall Street, they started to embrace memory technology aggressively. And then in late 2010, in late 2000, you have companies like Google, Baidu start to embrace memory technology aggressively. And now it's the rest of the world. It's like us. So this trend has been realized by many. Say, for example, you have Spark, you have Hana in-memory database, you have Cloudera Impala, but the issue is still not solved. So we're still missing a solution for the storage layer. So Tachyon fill the gap. Tachyon enable reliable data sharing at memory speed within and across computation frameworks or jobs. So how does Tachyon work? And so from a high level, here are two features that we provided at the beginning. So one feature is a memory-centric storage architecture, and the other feature is lineage in the storage layer. And there are many more features nowadays, but I'm going to talk about those briefly in the later slides. So here's the architecture of Tachyon. It has a single master which keeps tracking the location of data, as well as monitoring the status of every single worker node. And also has a workflow manager which manages the lineage information. On every single worker node, we run the Tachyon worker daemon, which manages a local space, as well as responding the remote I/O requests. And beyond the Tachyon worker daemon, we also run a RAM disk, which store the real in-memory data. And then when you have the Tachyon client, and also when you have the locality, you access this RAM disk directly without going through the worker daemon to guarantee the memory performance. So that's the worker side. And of course, the worker also periodically reports to the master about his status using the heartbeat. And then after the architecture, we also have the lineage in Tachyon, which basically describes the relationship among different files or data inside the Tachyon. In this particular example, you can see, say for example, you have a file set A, and you have a Spark job with A and generate B, and then you have another Spark job with C and generate D, and later on you have a MapReduce job with B and D and generate E. And Tachyon remember this information reliably, and this means that when this application like Spark jobs, MapReduce job when they try to write to Tachyon, they only need to write a single copy of the data inside the Tachyon space, Tachyon's memory. And then if any data got failed, Tachyon will be able to relaunch the necessary computation to get the data back. That's how the lineage works in Tachyon. So say in file set E failed, Tachyon just use B and D and MapReduce job to recompute it and get it back. So that's a basic, very high-level overview of the Tachyon project. And then let's talk about some use cases. So let's first use Spark as an example, how Tachyon works with Spark. So Spark is a fast and general engine for large-scale data processing. So it's great. It has been deployed in many companies, but there are still issues cannot be resolved using Spark. Say, for example, the first issue. So in many companies, you have this complex data analytics pipeline. And the way you do it is you have many jobs inside of it. So one job's output will be consumed by another job. And the system use like Amazon S3, like use Apache HDFS to do this data sharing. So in this particular example, on the left side, the Spark job 1 writes the data into the storage and loaded by the Spark job 2. So even though a single Spark job computation could be fast, but the whole pipeline is still very slow because the sharing process is slow. That's the first issue. And then the issue is furthermore complicated. Say in your cluster, you may have more applications, like more than Spark, you have MapReduce applications. How to share the data efficiently among these different computation frameworks is a harder issue as well. So with Tachyon, basically the way we address the issue is that basically we just use Tachyon in the middle, and these applications just interact with Tachyon to get a memory speed. So you can have the very fast memory speed data sharing, so the problem will be resolved. That's the first issue. And the second issue is in many in-memory computation engine nowadays, like Spark, they use the same process for the storage engine and the execution engine. So then you have the issue that if the storage engine crashes, you also, if the execution engine crashes, you also lose the data in your storage engine. So you either recompute it or load the data again from outside storage, which could be time consuming. And in this case, the solution is also put the Tachyon in the middle and put the data in Tachyon. In this case, if the execution engine crashes, it's still fine. You have the data in Tachyon, and next time you can load it from Tachyon at a memory speed. And the third issue is consider a simple example. Like you have two different applications, like two Spark jobs want to process the same data. So how do you do this? Nowadays, you have to load the data into different JVMs, into the different applications. Then you have the in-memory data duplication issue. And also, these applications run on top of JVM, you have a serious garbage collection issue when you have a lot of data, which can screw up the performance. And how do we solve this issue? So still we have the data set in Tachyon space, and these different applications, they can all load Tachyon's memory at a Tachyon space at the memory speed. And therefore, there's no in-memory data duplication. And also, these applications, they load the data from Tachyon's memory as the off-heap storage. You have much less garbage collection issue as well. Great. And here is a production use case. Say this is a public use case. Baidu, which is a dominant search engine in China, say they use Spark SQL on top of Tachyon, and under Tachyon they use Baidu file system, and you use Tachyon to manage two layers, both memory layer and HDD layer in the compute cluster, and then they use Tachyon to manage more than 100 nodes. Now it's like around 200, and more than 1 PB storage space. And when they use Tachyon, they have 30 times performance improvement. So one query, like the example they gave normally is that there is one query, so which it took like 1,200 seconds to process, which is like 20 minutes, and that's with using MapReduce without using Tachyon. And then they switched to Spark, and then the time reduced to 300 seconds, so which is 4 times faster. And then they add Tachyon into the picture, and they further reduce the time to be like 10 seconds, so which is another 30 times faster. So in total, it's like 100 times faster. So that's the use case, production use case by Baidu. And then there's another use case. This is the company, this SaaS company. They are using Impala on top of Tachyon, and under Tachyon, they use S3 as a persistent storage, and they use Tachyon to manage both memory and SSD, and they got 15 times performance improvement. And so that's the second use case. And the third one is an oil company, and they also use Spark on top of Tachyon, but under Tachyon, they use cluster file system, and they use Tachyon to manage memory only. And this enable Tachyon to manage data in a to analyze data in a traditional storage system. And the fourth one, this is another SaaS company, and they run Spark on top of Tachyon, and then underneath they run i3 storage. And they use Tachyon to manage SSD only, but they also have elastic deployment for Tachyon as well. And that's some use cases in Tachyon. So the next section, I'm going to talk about the new features in Tachyon, which we developed. So we just announced the Tachyon 0.8 release in October 22nd. And this is our release. We have a much longer release note describing the features. But now I'm going to briefly talk about several of them. And also we have maintenance release 0.81 and 0.8.2 recently as well. You can check them out. So first of all, it's a fast-growing ecosystem. So now you can use different frameworks on top of Tachyon and also enable workloads on different storage. So what does this really mean? So to the underlayer storage layer, so the benefit of using Tachyon is, first of all, it enables new workloads you can do on top of different storage. Secondly, it boosts the performance significantly. That's the benefit to the lower layer. And to the upper layer, for these different types of frameworks or the users, by using Tachyon, if you program against Tachyon, firstly, it enable you to access data or store data in many different types of storage. So you just one interface, you can access them all. So that's the first benefit. The second benefit is that by using Tachyon, you can also get the significant performance improvement, like the examples I mentioned earlier, like Baidu, the improve performance by 30 times. And on top of that, you can also share the data among different frameworks efficiently. If you have the environment that's going to be more than one jobs or more than one frameworks, now or in the future. And also, just one point I forgot to mention, and for the underlayer, you can access different storage systems at the same time in a unified namespace, which I'm going to talk about in a bit of detail in the later slides. That's the benefit of using the system, of using Tachyon system. So second feature is that we have the tiered storage concept. As you can see, you have memory in the normal storage hierarchy, you have memory, SSD, HDD. To the bottom, you have a larger capacity, but it's slower. And to the upper, you have the faster access, but you have less capacity, and it's more expensive. And now Tachyon manages more than DRAM. So we can manage SSD, HDD all at the same time. So you can have a much larger space. Say, like in Baidu example, they have PBs of space managed by Tachyon. This is tiered storage concept. And of course, you can have the policy to manage these different layers. For example, how to evict data from upper layer to lower layer, and how to allocate space in the same layer, or to the promote data to the upper layer. It's all policy based. And you can configure the storage tiers in different modes as well. You can say, I want to use memory only, I don't use Tachyon to manage memory only, or use Tachyon to manage SSD only, or memory plus SSD, all different type of tiers configuration. And also, this is the policy I mentioned. And you can evict the data to the lower layer, promote to the hot data to the upper layer. And this is pretty important because the different the companies that often have some data more important than other data. You want to keep those data in the upper layer as well. So that's the tier storage. And another important feature is the transparent naming. So this feature means that, so you can see Tachyon have Tachyon namespace, and under Tachyon you have the under storage, say HDFS or Amazon S3. And you need to configure Tachyon paired with A or more than one persistent storage. And previously, the Tachyon stored the data in a persistent storage using some naming convention only understood by Tachyon. So now we change it. Say you put the data in Tachyon. Say in particular example, you create a folder called data in Tachyon, and you create a file called reports, and you create a file called sales inside of the data folder. And correspondingly, in the under storage, similarly you have the folder called data, and you have another folder called reports, and the file called reports under data folder, and you have a file called sales under the data folder as well. So this is very important because now beyond using Tachyon and using different ways to access data through Tachyon, on top of it, you can also access those data using other systems, like some other applications access the under storage directly, just in case some APIs are not supported by Tachyon yet. But if you want to get the performance, of course, we can propose other APIs. You can access those data as well. So that's the transparent naming. And beyond this is the unified namespace, which is a very important feature and critical in many environments as well. So you can mount multiple under storage system in Tachyon namespace at the same time. It's on the fly. And we can share the data access across different storage systems. And this particular example, as you can see, like you can mount the Tachyon root namespace in the HDFS, like using HDFS. And then you say, okay, for the data folder, I want to mount it like I want to mount a S3 storage onto the data folder, and you can access, and from application perspective on top of Tachyon, they only see the Tachyon namespace. They don't need to worry where the data really is. So they virtualize this namespace in a unified way. And we have some additional features as well. Say, for example, you can say previously in Tachyon, you can only do local Tachyon namespace, no local Tachyon write, but of course you can always write to the persist under storage all the time. But now we also support remote write. Say, for example, when you have the local space is full and you haven't evicted the data out yet. So what the system can do is to write to remote Tachyon storage like transparently to the upper application. So, and then another thing is we improve the deployment of Tachyon. So previously you can only do standalone Tachyon deployment, and now you can use one command to do Mesos deployment, Tachyon on top of Mesos, or Yarn deployment to run Tachyon, to launch Tachyon on top of Yarn, to be easy to be managed like in different cluster or production environments. And also we have the initial like security support, and in next release this will be enhanced as well. So this is some security feature we're going to have. And as I mentioned, you have this one command like deployment, and also we use Vagrant to to better like support deployment as well, say you can deploy Tachyon in Amazon S3 in virtual machines, all using one command. And this is very good for developers as well, because you can deploy Tachyon in your laptop, by using one command, and create a cluster environment, like several to virtualize it like several machines. So this is very important to developers as well. So also we have metrics can be reported for Tachyon clients, Tachyon workers, and Tachyon master. And this means that you can use your favorite like cluster monitoring tool to monitor how Tachyon perform or how healthy the Tachyon system is in your cluster. Okay, so that's basically the features, new features we have in Tachyon in the most recent release. And next section, what I can talk about is how to get involved with the Tachyon system. So you can see we have a pretty big like ecosystem, and we welcome like users and collaborators. Say if you are users, you can if you have any question, you can go to our user forum to ask questions, and of course you can email us as well. And also from the collaborating perspective, there are different ways you can have, like if you are a framework developer, you can integrate your framework better with Tachyon. In that case, you will have better performance, and also access different storage easier as well. And below Tachyon, you can build more efficient connectors between different traditional storage with Tachyon as well, to make your storage being accessed by more different workloads. And of course, if you want to develop Tachyon system itself, it's very welcome as well. So we have a lot of Jira tickets in our Jira system, and you will have new contributor tickets like beginner, intermediate, and advanced. So we have for different levels. And in the end, we have these slides, we have these links if you want to know more about Tachyon. So you can try Tachyon. You can try Tachyon going to our website. You can develop Tachyon. This is our GitHub. You can, if you come to the Bay Area, we have meetup websites. Our last meetup have more than 300 people signed up. And this is our company website, and that's my email. That's pretty much it. And I'm happy to take questions.
I know. There is one. Don't go.
Hello. I wonder.
Hello.
I wonder how you deal with Kerberos authentication, DSCL, with the HDFS system and Tachyon.
How do I deal with?
How do you keep the access? Do you have issues, or is it correctly working?
So I'm sorry. So how do I deal with
when you mount your HDFS? How do you keep the SEL within the Tachyon? The users, the search mode, and so on. The right defined in your systems from HDFS to Tachyon.
Yeah. Okay. Oh, I see. Okay. Okay. So how, if you mount a volume, how do you keep the ACLs? So yeah, so that's a great question. So for now, when you mount onto storage, so at the Tachyon layer, we cannot keep the ACL. But in the following release, like in 0.9, as you can see, I mentioned earlier, we have the initial security report support for 0.8. But for 0.9, we are going to have a much better story there. But now, if you mount under storage, basically the data will be able to be accessed by anyone.
Okay. The second question, how do you deal with quota?
How do I deal with what?
Quota.
Quota, yeah.
Limitation.
So, yeah, that's a great question as well. How do we deal with quota? So, for the under storage has their own quota limitation. So that's their story. But from Tachyon perspective, the short answer is now we don't have a quota system. So basically, anyone when they write into Tachyon, they are treated as they use one single quota, which is like capacity of the Tachyon system. But like we also have the quota on the management on our roadmap. Thanks for the question. That's a great one.
Anybody else? Doesn't look like. Yeah, actually, by the way, actually, I think there is no other questions, so I guess we're done.
Okay.
Wait. Still one.
Hello. As far as I understand, Tachyon is memory, like cache memory for file APIs. And how do you deal with cache invalidation, memory invalidation?
How do we deal with
memory invalidation?
Memory allocation?
No, invalidation, but it's not really a caching system, actually. It's persistent behind.
So I didn't hear the last word. How do we deal with
let
caching?
me type it in. So, there's a massive problem with cache.
I can hear you clearly, Andy, when you are here. So caching invalidation. Oh, I see. So first of all, Tachyon is not a caching system. It's a storage layer, and we provide a file system API. So if you like, you can choose to use Tachyon as a caching system, but we provide functionalities much more than caching. Regarding the invalidation, so the semantics we're facing now is the under storage we're seeing is write-only semantic. Say, for example, basically, if you mount, the space will be managed by Tachyon, right? So in that case, we do not expect like a file update, those type of operations. And this is true, this assumption is valid. Say, for example, for systems like Gluster, for systems like HDFS or Amazon S3 or OpenStack Swift. So that's our assumption. And if you really modify the files, and for now we cannot do much about it, but we may have the mechanism to detect that later on. That's a great one.
Anyone else? Yeah.
Hello. In an underlayer system, how do you deal with alert if you lose one or if it's getting too slow? No, the underlayer.
Oh.
Andy, can you repeat the question?
No problem. I'm going. So, how do you deal with latency with the backend underlying system?
I see. Yes. So this is a great question as well. So when you deal with write, there are majorly three different ways in Tachyon. So one way is if you don't care about the persistency, you say, I only want to write into Tachyon space. If it's gone, it's gone. That's one way. The second way is that if you want to say, I don't care about the performance, I can choose, I write data into Tachyon. In the meantime, I also write data like synchronously, like Tachyon to write data into the under storage. In that case, you have a slower performance, like not very slow, but the same performance as using under storage directly for write. But in that case, you also have the persistency as well. That's the second type of write. And third type of write is that you use the lineage feature or asynchronous write feature in Tachyon. So basically, you use the API and you say, I write into Tachyon, and Tachyon will asynchronously flush the data into the under storage. And you want to call the lineage API to guarantee the fault tolerance. That's the third way. So basically, there are different ways. And depends on the environment and the requirement.
Yeah, I guess the question is that if you're in a streaming environment, right, and you don't have really this kind of Lineage capability, you cannot really ask back the data that you had, right? So if you lose the connection with, let's say, HDFS behind, and you don't have this capacity to get back the data from the sources.
Oh, I see. You're saying the mount point is lost.
Yeah, let's say it's lost, yeah.
I see. So for now, we don't have a solution there. But like the assumption now we have is, say if the one mount point is lost, so all the storage in a mount point will not be accessible by the upper layer. But the assumption we had was because it's a persistent storage layer. So normally the data should be still there in the under storage because that's their whole job. But if in any way, like data is the network is down, so we cannot access data temporarily in that perspective.
Cool. I may have one question. When you read data, so you can cache directly data from Spark to Tachyon, right?
Yes.
Yeah. And you can save it. Is there an easy way to read the data back from another Spark context right now?
Yes. So there are majorly you can say two different ways for Spark to interact with Tachyon. So one way is you use like Tachyon to cache the RDD in a Spark format, like in Spark internal format. So in that perspective, you could say like Spark RDD.cache or persist, and you can say off-heap, and then the data will be put in Tachyon directly. But that's a temporary storage in that perspective. And that data cannot be accessed by another storage Spark context at the moment. That's one way. And the second way is you can use Spark to interact with Tachyon and see Tachyon as a file system and interact Tachyon as a file system. You still will get a performance benefit. And in the meantime, it's much easier for other applications to access the same data because it's just a file from the outside perspective.
Indeed.
Yeah, you can use Spark to read a file, load a file, save a file, and other applications save a file, load a file, whatever they want.
Yeah, so the idea is to have a data source API implemented in Spark, for instance, where we can access it. And we may also store it as Spark case, so we keep the schema there.
I see. Yeah. So data source API is another one. So we're also investigating that part as well. That's a great one. Yeah.
Okay. We're done? Okay, looks like. Cool. Thank you, HY.
All right. Thank you, guys. Yeah.